Okay, 3:10, so let's get started. Today we're going to talk about power plants, fossil fuel power plants specifically, and next week the recorded lectures are also going to be about generation assets, but we'll get away from the traditional fossil fuel stuff. Okay, so this is a map that you guys may have seen before. This shows where all of the power plants, power generation, so not distributed level, but all the kind of utility scale generation throughout the country. The dots, the color of the dots represent the fuel type, and then the size of the dots represent how much capacity or how much power a particular facility can generate. And there are, certain trends that you'll see kind of geographically, right? And so in the Pacific Northwest, there's known to be a lot of hydro resources in blue. On the West Coast, you've got a lot of larger utility scale solar and some smaller solar on the East Coast. You've got orange natural gas kind of throughout the country. And then the other big one is the blackish gray dots are coal, which you'll mainly see more concentrated on the eastern side. And in fact, you won't find any in California. Actually, well, there technically is one, but it doesn't actually produce power for our electricity grid. The other one to note, so you guys will see a number of purple dots kind of throughout the country. Those will tend to be larger, and those are nuclear facilities. And there is one left in California. Does anyone know what this is?
Diablo Canyon.
Yes, Diablo Canyon. That's the last remaining nuclear plant in California, and it was originally scheduled to be decommissioned this year, but the legislature extended its lifetime a couple years ago. So it continues to operate today. Yeah, so, the other one that I forgot to mention, there's a big swath kind of in the Midwest of green, and that's wind resources, because wind tends to be, some of the best wind resources tend to be kind of in the middle of the country. Okay, and so any questions about that? We're going to spend time this week and next week essentially talking about these power generation facilities across kind of a wide variety of aspects. And the first thing that we're going to start with, so talking about fossil fuels, is about fuel extraction. Okay. So what are fossil fuels? These are fuels that are formed by the decomposition of dead organisms and exposure to heat and pressure from the Earth's crust. Okay, so dead dinosaurs. Because it's dead organisms, they contain high percentage of carbon, and under heat and pressure, that's going to let them form, these larger sort of carbon molecules. And so when we think about fossil fuels, right, it can come in three sort of general forms. You've got solid, liquids, and gases, right? And so solids, we're thinking about coal. For liquid, this is like crude oil, which you can, refine into things like diesel and petrol and gasoline and a number of other products. And then the gaseous form of fossil fuels, right, would be mainly natural gas, so methane. The liquid form is primarily used, or the bulk of that energy is going to be used in the transportation system, right? So that's how we power the majority of our cars and trucks, with gasoline and diesel. Although we do use oil in the power system, and we'll talk a little bit about that briefly, but generally speaking, that is a less used option. And so most of our focus today is going to be on natural gas and coal. So natural gas really is a very simple molecule. So it's just methane, CH4. But coal is kind of the opposite of that. It'll be very complex. I'll show an example in just a second. And we generally, so coal, unlike natural gas, is very, very heterogeneous, okay? It can come in many different sort of molecular forms. There isn't a standard like molecular formula for coal like there is for natural gas. And so we actually classify coal based on its energy density. And so we've got lignite, bituminous, and anthracite representing the kind of three broad categories of coal. And the easy way to remember this is lignite is the least energy dense, so L for low grade, B is for like a B grade for bituminous, and then anthracite has the highest energy density, and so A is like A grade. Easy way to remember it. Okay, and so as I was mentioning, right, so coal can be a very complex sort of solid hydrocarbon, but one thing to specifically note in here, right, as you look at this, example of a molecular structure, is that in addition to the hydrocarbons, it also contains impurities. It's got nitrogen in there sometimes. It's got sulfur. And so those impurities we'll talk about later as to how they can influence environmental outcomes as a result of combusting this stuff. And also it affects the sort of efficiency and energy density of the coal itself. On the other end of the spectrum, right, natural gas as methane, very simple, but what I will say is that if you were to, get a really good combustion process where you could isolate the methane, then technically it would be pretty clean. The only thing that you would get is CO2 and water as byproducts, but the extraction of it is going to include lots of impurities, of which you can process to some degree to try and remove them. But economics is going to play a role into kind of just how much you do that, right? And so you don't get rid of all the impurities at the end of the day. All right, and so as I was mentioning, you've got a range of energy densities. If you remember from last class, we had that little example of like, how much energy is in a kilogram of coal. And so I think I said, probably on the order of like 30-ish megajoules per kilogram. And so that would be more on the sort of higher grade bituminous anthracite type of coal. But a lignite, getting down to the real dregs, you can get almost half, right, the energy density, or less than half the energy density of some of the higher grades of coal. Does anyone know what country has a lot of higher grade coal resources in the world? The US, yeah. So we're like, I was joking in the other class, we're like the Saudi Arabia of coal. Yeah, so there are a number of regions in the US that has, pretty high quality bituminous and anthracite coal reserves. Okay, so unlike coal, natural gas is a lot more homogeneous. Its energy density is in a much more narrow range, so we're talking more on the order of about 1,000 BTU for cubic feet. Okay, reserves. So this refers to the fuel that exists kind of out in nature, that we know is there and that is economical to essentially extract and process. And so when we think about reserves, so coal is about 1 trillion tons. That's equivalent to about 33,000 exajoules of energy content. Just in the sort of chemical content itself, doesn't account for, the efficiency losses if we actually combust it and use it. Natural gas, 200 trillion cubic meters, or about 7,600 exajoules. And to just give a little bit of context in terms of what these reserves look like relative to our sort of energy consumption. So that's about 40,000 exajoules in total. And so what's 40,000 divided by 500? So 500 exajoules is about how much we consume every year. Excuse me. That's 800-ish years, right, of 800 years of fuel use that we can use. So this is actually lower than that, right, because actually these guys, you can't get all of that energy at 100% efficiency, and so it'll end up being right less than 800 years of use. And to just give a little bit of perspective in terms of what those reserves look like relative to all the other sort of fuel classes, looks something like this. The numbers here are actually a little bit different, but our annual global consumption is something like that. And then the fossil fuels and nuclear, so all of those are the sort of total reserves, and then for this renewable stuff, this is what's generated sort of annually. And so that gives just a little bit of hopefully sense of scale in terms of what our resource availability is to provide our needs, right? And yes, this looks very big, but at the same time, if you'd need to cover the entire Earth in solar panels if you wanted to take advantage of that, which you wouldn't need to. Yeah.
So this, I guess I'm not sure what to call it, plot seems to indicate it's energy consumption, not energy availability.
The consumption is just referring to that little blue, rectangle
Gotcha.
right at the top. That's how much we use.
Every other shape is just sort of a,
What's-
how much we have.
Yes. Yeah. Exactly. These four are how much we have, and these ones here are how much we have annually,
Okay.
because they're renewable. Any other questions? All right, so coal extraction, pretty straightforward. So coal beds exist out in nature. These are sort of pockets that contain coal in the form that essentially we use it. There isn't a huge amount of processing that needs to happen after the sort of extraction. There is some kind of filtering and that sort of thing, but the processing is fairly straightforward. And so this is just a diagram of a couple different sort of mining methods that can be used to extract the resource from these coal beds. And of course, there are sort of associated damages from a lot of the mining practices. And so strip mining, for example, is a very common form of extraction where you essentially kind of strip away at the land in layers so that you can continuously get to different sort of coal beds that are embedded in the land, but unfortunately it leads to a lot of sort of localized environmental damages. Okay. For natural gas, there is the form that we sort of traditionally think about in extraction is known as conventional gas. And so the way this works is you essentially drill straight into a pocket of gas, and you are able to sort of extract it and process it directly. And so that had been kind of the standard way of getting natural gas for quite a long period of time, until the sort of early 2000s, mid 2000s. There was this Texan engineer who came up with a sort of new method of doing gas extraction. Does anyone know what that's called? Fracking. Yeah, exactly. Also known as unconventional gas extraction. And so fracking is a different process where instead of going straight down and then extracting a resource directly from, let's say, like a large sort of resource chamber, essentially you drill horizontally out for very long distances. And you do that in this type of geological formation called shale that has lots of fissures where you have essentially pockets of natural gas. And what they do is they essentially pump this solvent. It's water that contains all these kind of crazy chemicals that help both dissolve some of the fissures and absorb the natural gas into the fluid, which they can then extract and process and get that methane out. And so the gas flows from the fractures into the pipe and then eventually gets collected. And so, whereas the conventional means of extracting gas, you kind of have to get these you have to get at these large pockets that are much more dense with the resource. Here, right, from a single surface, a smaller sort of surface area, you can spread out and be able to extract the resource in a pretty large radius. And one of the other things, so as a result of fracking, we started exploring the sort of potential for fracking resources in what is known as these shale plays. And so the US is actually pretty well situated and has a lot of fairly rich fracking resources. So that has led to a kind of large transformation in our electricity system. So when I think I showed a pie chart before, or in the earlier lecture about emissions, or maybe not, but does anyone know what the largest emission sector is in the US? Yeah, transportation. So if I had asked you that same question a decade ago, the answer would have been actually different, because the electricity sector, it's not that transportation actually grew so much, but actually the emissions from electricity sector decreased by quite a lot, largely due to the economics of natural gas and how it has essentially displaced coal as the sort of primary power producer in the country. Thanks to fracking, the prices of natural gas has dropped quite dramatically, and that has led to its ability to really outcompete coal as a primary sort of resource. Yeah.
So the natural gas that you extract is full of all sorts of impurities.
Yes.
How much of what we get from fracking is natural gas, or like is methane?
It is primarily going to be methane and oil, depending on the particular location. But I would say, fracking is mainly associated with methane. So all the impurities and stuff, that often is kind of collected in the water, and that leads to other sort of implications about how you deal with fracking water. And that's been a big sort of environmental debate ever since fracking started, 15, 20-ish years ago. There's a really big concern, right, about, you're like going past these water tables, and so what happens if your like casing breaks or leaks, and you get that really bad stuff into the water table. And there are these crazy videos of things like that happening, like in Pennsylvania, where people I don't know if you've seen this, you can turn on a sink and then light the water on fire. So there are these examples of that happening, which isn't great. And then as far as the water disposal, they don't really have a good solution for it. I think as far as I know, so you're definitely not allowed to just dump it into other water. They just keep them in these giant basins on site.
Like a
And
nuclear solution.
yeah, exactly.
You don't get as much out of it.
Yep. So fracking has a number of sort of big local environmental concerns. Oh, the other big one is the earthquakes. So particularly in Oklahoma, North and West Texas, where a lot of this stuff is happening. Like in the Barnett, I forget what this play was called, or the Woodford play here. They have reported. I've seen some papers about how they report something like 5 to 10,000 earthquakes between 1 to 3.0 on the scale every year now. So small quakes, but not ideal probably. Okay, any other questions about that? Or comments?
I was kind of curious, do they use evaporation ponds? Is that the method when they store it on land?
I'm not sure. I don't know actually the method of storage. Okay, so as I mentioned with coal, not too much processing needs to happen, some filtration stuff that happens, and then you do have some processing that typically happens at the plant actually to crush the coal down. But for natural gas, right, there is quite a lot that's gonna happen here, and so once you get it out of the well, you have a whole sort of separation process. So you get oil, and then you get your natural gas out, and then the water, the really terrible water, right, that separates all of this. And then that goes to a processing plant to help reduce some of those impurities that I was talking about. That goes to a compressor, which then goes to a distribution system to send the natural gas to sort of the end use places, right? And so that does include, so obviously to the power plants that we're going to talk about today, but also the distribution of natural gas goes to other end uses, right? Because we also use natural gas in industrial processes, commercial buildings, and even residential, water heaters, cook stoves, right? A lot of those use natural gas. And so natural gas transmission and distribution network kind of goes out to all of the end sectors. All right, any questions about that? So the next piece that we're going to talk about today is conversion. So we have the extraction of the fuel, and we're going to do kind of a quick aside we're going to do a little basics on how electricity is generated before we sort of match all of this stuff up, where we can then talk about how fuels are converted to sort of be used in this process of generating electricity. Okay, so like I mentioned, so this class we're not going to do like quantitative stuff. This is like physics and engineering light. So we're going to talk about this kind of qualitatively. And so what I'm showing here is a generator slash motor. And so this is, a generator is essentially a process in which I can take mechanical energy and turn that into electrical energy. Okay. And the way that you do that is you have two components. You have a rotor and a stator. It's pretty easy to remember, right? The rotor is the rotating part and the stator is the stationary part. So one of those has to be a sort of permanent magnet and the other has to be a wound wire. But it actually doesn't matter which one is the one that's moving and which one is the one that's staying still. There are examples of both of these that you can do. In this particular example, our coil is the thing that's moving, and our magnet stays in place. And essentially what happens is if you move a coil through a magnetic field, right, it's going to generate movement in the electrons of that coil, which is electricity. Right? And so I'm going to be spinning this through the magnetic field and then inducing a current to flow through that wire. So in order to do this, I need to have some kind of mechanical energy that's actually providing the movements. Okay, and so that is what that's how a generator works. And so basically, if I can get something to spin in some way, I can produce electricity. And then vice versa, you could do the same in the opposite way, and that's just the motor. You can use electricity to cause something to move. So a generator and a motor are actually exactly the same thing, just moving in opposite directions. Okay. Any questions about that? So how do we get from the fuels that we're talking about into providing that motion? Okay, and so the way that we do this is through heat engines. So this is a very sort of generic description, but essentially a heat engine is a way that I can take thermal energy, right? And so think about that, right? So how am I generating thermal energy with these particular fuels, right? You generate thermal energy through combustion, but I can turn that thermal energy into kinetic energy by manipulating temperature, pressure, and volume of a working fluid. So this is the ideal gas law that describes the sort of basic relationship of that fluid, which is, so PV equals nRT. So for those who aren't familiar, P is pressure, V is volume, N is a description of quantity, so number of moles. If you've remember this back in chemistry, R is a constant, and then T is temperature. And so the basic relationship here is that if something is heated, right, so temperature goes up, then that means that my pressure or my volume also has to increase. So one or both of those must increase. Okay, and when the temperature goes down, pressure and volume have to decrease. And so engineers are going to take advantage of this sort of principle in order to sort of build these sort of heat engines that's going to allow us to go from thermal energy into kinetic energy. Okay, so where are we getting that thermal energy from? Combustion, right? So this top equation, this is a generic equation for the combustion of a hydrocarbon, so of an arbitrary length, CnHm. So you combine hydrocarbons and oxygen, and you get a very exothermic reaction, which releases a lot of heat. And so the byproducts of that reaction are carbon dioxide, water, and then the heat that I was talking about. So I can plug in, natural gas, so CH4, and you would get this equation. And if you were able to get a very complete combustion process, then you would just release carbon dioxide and water, as well as that heat energy that we need. But as I mentioned, you've got lots of impurities that you have to think about as well. Does anyone know where do we get the oxygen that we need for the combustion process?
Air.
From air, yes. But is the air pure oxygen? No. So what's the most common molecule in air? Nitrogen. Yeah, and so when you have nitrogen in there, so at high temperatures, that can also react with oxygen to form nitrogen oxide. So this is a common thing that you have to worry about in combustion, particularly when you're doing combustion use and employing oxygen in the air. Okay, and we've got all sorts of other things, carbon monoxide, carbon dioxide, methane itself. So if you have incomplete combustion where you don't burn off all the fuel, you might actually release some of that input fuel. And a number of other bad stuff, N2Os, volatile organic compounds, probably very small amounts of sulfur, because there isn't much sulfur associated with natural gas, and a little bit of particulate matter, but the latter two are going to be quite a bit smaller with this particular set of combustion processes. But with coal, right, you've got all of those impurities that are trapped in the solids. That's going to give you all sorts of terrible byproducts of combustion. And we're going to talk a little bit more about this at the end of the lecture today in terms of what the impacts of some of this stuff is.
Could I just ask, what is the N?
So the
Just the
N,
coefficients then?
yeah, so the N and M describe the number of carbon molecules and the number of hydrogen molecules, and I leave it sort of generic to describe that you could use this process to combust any hydrocarbon. Yeah, and then it would just change all those numbers in terms of what you get out for carbon dioxide and water. Okay, so again, I'm not going to get into too much detail here, but the sort of heat engine that we typically use for a lot of these processes are turbines, okay? And so almost all of the electricity that you could think of that's produced worldwide is generated via a turbine at some point. So with the exception of like solar PV, most other electricity that's generated is going to be made from a turbine. And actually even solar can use turbines if there are forms of solar production known as concentrated solar production, which uses mirrors instead of PV, and they heat up water and it goes through a steam turbine. So even solar does this. So essentially the way this works, right, is we're heating up some kind of fluid that increases in pressure, and we take advantage of that pressure in order to essentially spin something. So with a modern steam turbine, looks something like this. You have kind of multiple stages of these blades that allows you to incrementally increase or decrease pressure and velocity. And that spinning that takes advantage of all of that pressure is the thing that actually powers the generator to produce electricity. So we'll start first with a coal plant. And what I have here is a description of a particular type of thermodynamic cycle. So what is a thermodynamic cycle? So this is a cycle that goes through multiple thermodynamic stages, and importantly, has to return back to its sort of initial state at the beginning in order for it to be considered a cycle. Okay, and so what are we looking at here? So I take some water, and then I can collect it with a pump and send it into a boiler. In the boiler, I can heat up that water and generate steam at high temperature and high pressure, and send it through a turbine. That turbine is gonna spin. What happens to that steam in the turbine? So it loses a lot of its energy, or I should say it transfers a lot of its energy. And so it cools down and it drops in pressure. We condense that steam back into water and then send it over back here to the initial state. Okay? And so this thermodynamic cycle, this particular thermodynamic cycle is known as a Rankine cycle, and that describes essentially the process of a steam turbine cycle. So you can work out the thermodynamics and see that there's a sort of maximum theoretical efficiency of about 64%. But we don't actually realize that efficiency in the real world. And so what I should mention kind of at the beginning, what am I talking about with efficiency, right? So this is the energy content in the sort of chemical bonds of that coal molecule, and when you combust it, right, you release that energy. How much of that released energy can I actually gather in the form of electricity? So about the maximum, right, is about 64%, and then the maximum that we see in modern day coal plants is about low 40s%, and you're not really getting more than that. And so 40% of that energy you can get in electricity. But that's a very sort of high number. Most modern coal plants are going to be more in the like mid 30% in terms of efficiency. Okay, and so this is a little schematic of what a simple schematic of what a coal plant looks like. So in the first stage, we've got this mill. So I take the coal. I don't know if anyone's ever been to a coal plant, but they have these big trains that come in and they just like dump the coal into these big hoppers that then you convey up into these mills. And so in the mill, the coal is ground down into kind of fine coal powder. And so why do we do that instead of just throwing in the coal? Yeah.
Greater surface area for combustion.
Yeah, exactly. And so when you grind it down into these little particles, you have a lot more surface area. And what that does is it allows the combustion to happen more efficiently and quickly. So we've got coal in here in a furnace being combusted. Okay, so that process releases thermal energy, and you can see there's this kind of pipe diagram. So essentially what you're doing is you're heating up water. It's actually in a boiler, sends it through here. So that heated up steam goes through the turbine, and the turbine rotates, spins either a coil or a magnet, and sends that in the generator to produce electricity. So you'll notice there's kind of an interesting thing in this diagram. So we actually have a closed system here of water, and the condenser is essentially powered by a separate loop of water here, which is where the water will sort of condense and then get sent back up into to get heated up from the furnace. And so why do we do this, right? And so I'll just quickly say, if you look at the sort of map of where all the coal plants are, you'll notice that they usually sit on sort of bodies of water, usually like rivers, and they take advantage of that in order, they use the river water, right, essentially to help cool and condense the water coming out of the turbine. And so why not just send that water through here? Why do we have a closed system? Well, what was that?
We have to treat river water before boiling it.
Yeah, so river water is gonna have lots of impurities and whatnot, right? And so you're sending that stuff through a turbine. Turbine's gonna get dirty. It's not gonna run efficiently, gonna degrade faster. You're gonna have to do more maintenance and operations on it. It's gonna cost more money. And so instead, you have a pure stream of water in the closed loop, and then you cool that through a separate loop that doesn't need to touch, the turbine or anything. Okay, and so that water source, that gets heated up, so it's cooler water that cools this down, it gets heated up, and so there's these cooling towers that you'll see, that's where the water vapor comes out of. And the cooling towers tend to be usually a little bit lower in elevation, or lower in height, I should say, than sort of the chimney stacks. And so this stuff, not a big deal if you're kind of standing next to, it's just water vapor coming out, but you don't want to be breathing out any of the stuff coming out of the chimney stack, which is where the combustion byproducts are actually exiting. And the chimney stacks tend to be much higher, right? Because for several reasons, there are pollution control technologies in the stacks themselves that help reduce some of the material that's getting emitted, and reducing some of the worst of the combustion byproducts. They also want to keep it at a certain height so that as the stuff gets emitted and it disperses, by the time that it reaches ground level, it should, in theory, be at lower concentrations that are more acceptable. Right? Okay, any questions about that? Yes?
So, do natural gas plants use steam turbines as well?
We'll find out in just a second. Yeah.
So the water in the closed loop, when it's heated, becomes steam, and then it's condensed back into water from the second loop?
Yes, exactly. Yep. So essentially the cooling process happens via an external source of cooling that doesn't have to be like clean or pure. Yeah. There's some environmental implications of like heating up a bunch of river water, but yeah, people don't talk about that one too much. Okay, so I want to talk a little bit about some terminology that we commonly use with power plants, particularly with combustion-based power plants. So the first one is a heat rate. So this describes the efficiency of a power plant. So I was saying, the maximum theoretical is like 64%, and then most power plants are 35, 40% for coal in reality. But in fact, the way that folks in the electricity and power sector talk about efficiency is through a metric called a heat rate. Okay. And so what is a heat rate? So this is the amount of fuel energy required to produce a kilowatt hour or megawatt hour of electricity based on the energy content of the fuel, right? And so heat rate here, so BTUs per kilowatt hour, or you'll also see MMBTUs per megawatt hour. And so the numerator is your fuel energy input, and the denominator is the electrical energy output, right? And fuel, we usually think of, right, in BTUs or MMBTUs, while electricity we usually think of in terms of kilowatt hours or megawatt hours. And for that reason, the heat rate kind of came into play, as opposed to keeping them both in the same units and reporting them as like a percentage efficiency, which you could do, but the sort of parlance in this sort of discipline or sector is to think about things in terms of heat rates, right? So very much analogous to, you know, like a miles per gallon, right, in terms of efficiency. That's not really, that wouldn't be a proper efficiency units to think about, right? But the way that we use MPGs, it's common knowledge, and so that's what people use. And the way that we use it is thinking about the relative MPGs of different vehicles, right? And so in the same way, the way you want to think about heat rates is what is the heat rate of a particular generator or power plant relative to a different one, right? And so you want less of a fuel energy input to produce the same amount of output, right? And so a lower heat rate is more efficient than a higher heat rate. Here in this chart, this shows a distribution of heat rates for different power generating facilities in the country. And so these two are coal. So for bituminous and subbituminous coal, steam turbines, the heat rates look like this. And then here you've got natural gas. So don't worry about this stuff. We're going to talk a little bit more about natural gas heat rates in a little bit. Right, and so if you did want to translate this into an efficiency, all you would need to do is put in the sort of conversion. Well, you'd want to take the inverse, right, because efficiencies are usually output over input, and then you'd want to convert your kilowatt hours or BTUs to the corresponding units. And so the way that you can do that, it's just this number, 3412 divided by your heat rate will give you the actual efficiency number that we're talking about earlier.
And that's as long as you're using BTU and kilowatt hours?
Yes. Someone asked me about this yesterday. Does everyone use heat rates for BTUs per kilowatt hour? And I wasn't actually sure. We looked it up. So if you're European, you'd be using, or the rest of the world, you'd be using megajoules per kilowatt hour instead of BTUs, in which case the heat rates are going to be a little bit different. So the relative stuff still doesn't change, right? And so you still think about things relative to one another. This would be, again, analogous to like an MPG versus like a kilometers per liter that the rest of the world would be using. So either one is fine, just don't mix and match them because then you'll get in trouble. Okay, how much and how often do plants run? So this describes two other sort of common terminology that we'll want to be talking about with power plants. So capacities and capacity factors. Very important to keep these, to kind of nail these down, keep these separate and understand what they mean. Okay, so capacity describes kind of the maximum amount of power that a generator can produce in any given moment under whatever operating conditions it needs, okay? And so capacity is in units of usually megawatts, right? So when we talk about power plants, we're usually on the megawatt scale. And to just give some sense of scale here, right? So like a residential rooftop solar might be on the order of like 1/100th of a megawatt. Coal plants are going to be, coal plants and CCGT is a combined cycle gas turbine. We're going to talk about that, what that is in a moment. Those are going to be on the order of a couple hundred megawatts. And then wind farms are going to be, on the order of tens to low hundreds of megawatts. So that all describes kind of the instantaneous output capability of a power plant. And the reason why we talk about capacity factor as a measure is because not all power plants will have, power plants may have the same capacity but operate very differently over time, right? And so this is the measure of how it might actually be used. And so the way that we calculate a capacity factor is just, okay, what is its capacity and for how long do we want to measure and how much energy was generated over that period, okay? So if you have a capacity factor of 1, that means you are always on, right? So if you are generating a power plant only half of the time of the entire year, then your capacity factor would be 0.5. So pretty straightforward. And to give some sense of why this is important, right? So we could have a, 500, or okay, I'll do it with the easier numbers, even though it doesn't necessarily make sense for the fuel, but let's say we had a 100 megawatt nuclear plant, right? On average, a nuclear plant might be on for 92% of the time, compared to a gas plant, which would be on 60% of the time, compared to a coal plant, which would be on 50% of the time. And so when I say, oh, I have a 100 megawatt nuclear plant, the amount of energy that it produces over the course of a year is going to be different than if I said I had a 100 megawatt coal plant, even though the capacities are the same, right? In green here, we have renewable sources, and these ones are not going to be on all the time, right, because of the resource availability that powers these particular generators, right? And so for solar, the sun doesn't always shine, and for wind, the wind doesn't always blow. And so these are pretty typical numbers that you might expect from a wind farm or a solar farm. You get only 25% of its rated capacity when we think about the energy that it produces over some amount of time. Okay? Any questions about that? Okay, so the last bit of terminology, so ramping and startup. So this is thinking about how fast a power plant can change its output or turn on and turn off. So ramp rate is about the speed of change in the output. We often think of this as percent of the capacity per minute, right? And so if you had like a 200 megawatt coal plant, and I can ramp up by, let's say, 20 megawatts per minute, then that would be 10% of the capacity per minute. So the flexibility for your ability to balance load, so let's say a bunch of people turn on their lights at the same time. Now you've got to turn on a bunch of power plants. Well, some power plants are going to be better at responding to that event than others, right? The other one to think about is startup time, and so that's time that it takes to sort of sync up and essentially meet the load operation of your generator from shutdown. And so you might shut down your generator for any number of reasons, for maintenance and operation issues, right? And once you do that, you can't always just turn it back on right away. There's certain procedures in terms of being able to do these starts, and so there's things known as like a hot start or a warm/cold start that have to do with kind of the downtime of your generator and then how long it takes to get back up. And so here, I'll get some sense and ranges of these ramp rates and start times. Generally, we're going to say like a turbine, a gas turbine is going to be a lot faster And we'll see why, because of the way that the combustion process happens, than a coal plant, right, which actually has to boil water in order to send it through a turbine, and so that takes time, versus a nuclear plant whose process takes kind of even longer. Yeah.
I've heard the phrase dispatchable thrown around for certain resources.
Yep.
Does that describe peaking, I guess, resources?
So dispatchable just means that I can tell a power plant to kind of turn on and turn up or down. And so all of this stuff technically is going to be dispatchable. Things that we wouldn't consider dispatchable would be like solar power or wind power, which is just on when it's on when the resource availability is there. But dispatchability, we're going to talk a whole bunch about this throughout the course. There are things related to the market for why we do the dispatch, but there's also physical attributes of the plants themselves that make them better for certain types of uses. So base load, intermediate peaking. We're going to talk about what that means later, but all of this would be considered technically dispatchable.
How is nuclear dispatchable? I always just assumed it was kind of a
Yeah, like
odd.
nuclear is a little odd in that way, but technically an operator could go to nuclear facility and say turn down, go down a little bit, go up a little bit, or turn off, right? That's yeah. People. It's technically dispatchable, but a lot of folks wouldn't necessarily think of it as a traditional sort of dispatchable resource.
Because like you're still burning the same amount of nuclear fuel, you're just extracting less of the energy.
Yeah.
I don't know.
Well,
I guess you pull the fuel rods out-ish.
yeah. So in a nuclear plant, you are able to control the rate at which the nuclear reactions are happening, right? And so that is one of the things that is an attribute of dispatchability. But the speed at which that happens is going to be slower and less responsive.
Okay.
Yeah. Okay, so this is kind of a reference table. You guys don't need to memorize this stuff, but I'm just gonna walk through. So for all of those terms that we just talked about, these are kind of the ranges and values that we see for coal plants, right? So heat rates, we're talking on the order of like 10,000 plus BTUs per kilowatt hour. So keep that in mind as we compare other things later. The unit capacities, we had talked about this in the first lecture, generally tend to be a little bit on the larger side, so hundreds to high hundreds to gigawatt size for coal plants. Capacity factor kind of depends on what era we were talking about, right? Because coal was less, it is less now than it was 10, 15 years ago. So we'll say kind of 50-ish% capacity factor. These are the ramping and startup times. And kind of related to this capacity factor thing, so it used to be more sort of base load, but now is more kind of intermediate. Okay, let's take a quick break. I'm running behind just a little bit, so why don't we say 3 minutes and then we'll get back into it. All right, let's jump back into it. So next up, we're going to talk about natural gas plants. Okay, so natural gas power plants also use a turbine, but they don't use a steam turbine in the same way. So this is a gas turbine. Does this look familiar to anyone? What does this look like? A jet engine, yes. So a jet engine is a gas turbine, and so you could, in fact, tear the engine off of a jet and then connect it to a generator, and you would have a natural gas power plant. It would work totally fine, but you wouldn't be able to do that in reverse for obvious reasons. Well, no. Okay, so yeah, it would be using a different fuel source, but you could probably put in natural gas. It would not be as energy dense, and so you probably wouldn't use that to fly a plane, but to generate electricity, probably fine, I think.
Well, when it's injected to a jet engine, it actually turns into a mist, so it's kind of like a gas.
Yeah, yeah. I just don't know the operating dynamics of something that's combusting jet fuel versus natural gas. I think I think you could make it work. Okay, but the way this basically works is you suck in air through here, through these fan blades, and they progressively sort of increase the pressure until you're in the middle chamber here. There you are injecting your natural gas fuel, creating a fuel-air mixture, and then combusting it. That creates tremendous heat and pressure, and that's going to be what's actually spinning this thing as it gets sucked out back this way, reducing the pressure, and you have a byproduct of hot exhaust gases coming out here. Okay? And so you're able to get your turbine assembly to spin, which means you can generate electricity via a generator. And so the thermodynamic cycle here is known as a Brayton cycle. I don't know actually what the maximum theoretical efficiency of the Brayton cycle is, but in practice you're getting kind of in the mid to high 40%, right? Which is a little bit more efficient than coal, right? We were talking about more on the order of 35 to 40% for coal, where this is more like 45 to 50%. Okay, and so this is a very basic schematic process of what's happening here. Okay, and so we have our byproducts of combustion that we talked about, and what else are we getting out of this turbine? Yes?
Steam.
No steam.
Oh,
No
heat.
steam, right? This is just gas and air combusting into, CO2, water, and a lot of heat, right? So, turns out, well, we could take advantage of that heat, right? So this is a schematic of a combined cycle power plant. And so why am I calling it combined cycle? Well, actually, so here I've got my gas turbine, right? And so this is going to be connected up to a gas generator to produce electricity after that combustion process. But then the hot exhaust gases are going into boiling water, which I then can send through a steam turbine, right? A la the same kind of Rankine process that we use in a coal plant. And so I can combine the exhaust gases from the Brayton cycle to be used in a Rankine cycle, where the heat generated is from combustion of gas as opposed to combustion of coal. So here I have my gas turbine injecting in natural gas, combustion, and that is powering a gas turbine generator to produce electricity. And these hot gases are powering and heating up a closed loop of water here. which then goes through a steam turbine, powering a steam turbine generator and producing electricity. And so some of that heat that normally I would be wasting, I can then take advantage of in order to produce even more electricity and increase the overall efficiency in terms of how much of that energy of the original natural gas molecule I'm able to take advantage of. And this will go through that loop that I talked about before. So here your efficiencies can be 60, 65%, right? And so substantially more efficient in comparison to the coal process, which can't do something like this. So when we jump over to this slide about the sort of operational attributes of our natural gas plant, we'll see that, okay, if you do a simple cycle gas turbine, so this is known as OCGT, simple cycle, where you only have the Brayton cycle and not the Rankine cycle, your heat rates are actually kind of on the same order as coal, maybe slightly more efficient, right? So we're probably more on the 9,000 than the 11,000. But when I do a combined cycle, I can get much better. I can get 6,000 to 7,000 BTUs per kilowatt hour. Okay, the unit capacities for these simple cycle ones tend to be smaller. And so why is that, right? And the reason that we would have units that do this is that they are actually taking advantage of the ability to ramp up very quickly, right? And so if you look at the ramping startup times, right, you don't need to boil water. You just send in natural gas into your turbine, combust it, and you're able to start up very quickly. You're getting 5 to 10% of your output per minute. Okay. And so the use case of simple cycle turbines is there, but maybe it's a little bit narrower. When you're talking about wanting to be on all the time and the economics associated with that, you want to be combined cycle. And that's why the capacities of these combined cycle plants are going to be the ones that are sort of on the larger end, right? So we're talking 400 up to gigawatt size combined cycle power plants. And so these guys who are producing kind of niche services, and we'll talk a lot more in detail later on about some of those niche services, capacity factors are going to be lower, whereas here, combined cycle, these are increasingly becoming more kind of like base loady type power. Okay, and you will see the startups and ramp rates of the combined cycle is going to be slower, right? Because we have to boil water and be able to start up our steam turbine in addition to the Brayton cycle part of it. Okay, any questions about natural gas? Great. I'm going to talk really briefly about oil generators. So these are a thing. I did mention right at the beginning of class, right, the vast majority that we think about with fossil fuel for electricity generation is coal and natural gas. But oil does exist, and this is essentially going to use the same process as coal, except that you are combusting oil to heat up the water in the boiler as opposed to combusting coal. And here you'll see the operational attributes. So the heat rate is actually not so bad, right? So this is kind of in the same scale as natural gas, as coal. So why is it that we don't use oil plants very often? Well, that's going to play more into the economics of it, where the fuel cost relative to our other examples is going to be quite a bit higher. And so as a result of this, these guys really only turn on for small portions of the year when you've got a lot of electricity demand and you need to start turning on kind of the last resources. And so these are called peaker plants to deal with those peaks in electricity demand. And they have all around pretty terrible attributes.
Are those OCGT plants, are those used as peaker plants as well?
Yes, and so those plants are going to be, so oftentimes they're going to be peakers, they're going to be reserved for other reasons as well, but those guys are going to get turned on before these guys are going to get turned on. So these guys are truly the like last takers, usually. And a lot of the reason why these guys are still around is actually historical too. And so we're going to revisit this curve a couple times throughout the course. This is kind of a peek at what was built historically. Okay, and so you can see kind of in the 70s, 80s was this big era of construction and deployment of a lot of power plants. You'll note in those time periods, we've got a lot of brown, which is coal, some natural gas, and then some nuclear as well, so in red. And you can see that red piece, and we're gonna talk a lot more about nuclear in the recorded lectures next week. Those kind of stopped in the late 80s, early 90s. But most of the coal plants that we see built were in the sort of 70s, 80s, even 60s time period, and not so many happening kind of anymore. We've got a huge peak here and spike of natural gas plants, and that corresponds with fracking, right? So we talked about in the mid 2000s, that's when natural gas started to become a much sort of better resource or economical resource for fossil fuels. And kind of following that, in the 2010s, we see a little bit more visible growth in renewables. So starting with wind, and now in more sort of modern day, a lot more solar as well. And you can see how that's reflected in sort of the cumulative power supply, where coal starting to decrease right at the end here, corresponding to a large increase in natural gas. Okay, any questions about that? So next we'll talk about some of the economics related to these fossil fuel plants. Okay, so when you think about all the costs that are associated with a power plant, where do those costs come from? So the big one is actually building it. So overnight capital cost. So this is a kind of term to understand the cost of a plant that excludes the financing. This is kind of like if you were to build it overnight, kind of how much would it cost? So that's usually the one big kind of upfront cost. And then you've got sort of annual costs having to do with upkeep and use of your facility. Right, and so fuel costs is ongoing, so the more you use it, the more your fuel costs will increase, right? And that's usually the sort of most dominant cost when it comes to the variable costs of these facilities. You've got operations and maintenance, which we'll divide into two categories. You've got fixed and you have variable O&M. And then you have, if you were to do like economic analysis, lifetime and financing assumptions, like discount rates and that sort of thing. So we'll walk through the economics of our fossil plants through sort of each of these categories just to get some context and understanding of what that looks like. Yeah?
In the overnight capital cost, what do you mean by financing?
Right, and so if I wanted to build a power plant, in theory, I could go to a contractor or construction company or whoever it is that actually builds this power plant, and I can say, here's $1 billion, build me my power plant, right? And they would go and build it. But that's not really what happens in reality, right? You have to go and you borrow money, right? And so the financing piece of it is like how that loan gets structured and how you pay it back and how that relates to maybe operational and performance aspects of the power plant. So there's a lot that goes on there. And so for more simplistic reasons, oftentimes we will talk about overnight capital costs to kind of cut that stuff out and just understand what the like cost of the actual construction and material is. And I should say, like the reason why we might do this, right, is to provide better apples to apples comparison of different power generation facilities. So think about how am I supposed to compare like a solar farm, like a 100 megawatt solar farm, which would have very different loan conditions and financing conditions compared to like a 1 gigawatt like coal plant. And so the overnight capital cost is the way that people think about this to make those comparisons a little bit easier. Okay, so overnight costs. So we think about this structured in a way that is standardized to the capacity. So this is a dollar per kilowatt, right? And so if I wanted to build a gigawatt capacity coal plant, that would be $1 million. Your denominator would be a million gigawatts, right? And so that would cost me $3 billion to build a gigawatt coal plant, right? So this is capacity and not having to do with the like energy production in any way. Okay, and so these give kind of the relative scales of the costs, and you can see, one of the reasons why natural gas had become a lot more compelling is that the economics are a lot better here in terms of the capacity costs, and once coupled with the sort of lower fuel costs, started to make them a lot more sort of dominant as a resource that we see today. And even though oil-fired steam looks cheaper in a capacity basis compared to coal, remember that the fuel costs are very high, and so the economics tend to look not so favorable for these guys. This last row here, what CCS, does anyone know? Yeah, so carbon capture and sequestration. So this is a view into clean coal, if you call it, if you're able to actually do it effectively, right? Well, the CCS, the mechanism and the sort of infrastructure around being able to do that is actually pretty expensive. And so we estimate something on the order of, as much as double your sort of typical coal plant. So fuel costs, right? And so this here gives us a sense of the cost per MMBTU. But when I do it in terms of MMBTU, that's just the fuel content. It doesn't take into account kind of what I get out of the fuel in terms of efficiency. And so if I wanted to do a cross comparison in terms of how efficient or accommodating those sort of losses in the combustion and what I get out of it, your cents per kilowatt hour looks something like this. Okay. So there are ranges to these things, but the natural gas is going to be, on average, kind of on the sort of lower end, and the coal is these days going to be more kind of on the higher end. So it's not so much like, so it'll be more kind of like on the 1.5 for natural gas compared to maybe high 2s cents per kilowatt hour for coal. And then oil is just kind of terrible in terms of the economics. Okay, operations and maintenance. So as we talk about other variable costs, So FOM are the fixed costs. So these are the costs that you have to pay regardless of how much the plant operates. And so the plant could be on 100% of the time, or it could be on 0% of the time, and you'd still have to pay these costs. That's what fixed is referring to. So labor and staffing, right? So you got to pay the staff regardless of what's going on with the power plant. Routine maintenance, overhauls, taxes and insurance, and then environmental compliance. And so there are things of compliance that you have to do regardless of whether or not the plant is operating. And so these kind of constitute the totality of the O&M costs that you might face as a power generation facility. Or I think this should be most of the things. Variable O&M, so these are costs that scale with generation and are incurred when you actually run the plant. So these are all the costs to run the plant minus the actual fuel cost that you're using, right? Because that's like so big that it's typically considered in its own category and not in the O&M piece. So consumables and reagents. So this includes things that you might be using for like scrubbers, for certain chemical controls that you're going to be using as the plant is operating. Waste handling and disposal, maintenance from wear and tear, auxiliary power use, consumable water, and then, regulatory and operating fees. Okay. Yeah, so just some examples in O&M. So coal and oil generators, for let's say a sort of mid-sized power plant, you're going to need on the order of 60 to 100 full-time employees compared to a combined gas turbine, which has typically smaller crews on average, maybe 20 to 30 people for same size. You need all sorts of things for maintenance, like coal plants have to maintain these like ash handling systems. The byproducts of the coal combustion is a lot worse, and you just have to figure out ways to deal with that, right? And that costs money. This is the heat recovery steam generator system in a combined cycle. Someone's going in there and doing some maintenance operations. So what do those costs look like? Again, just a reference slide. You don't need to memorize this or anything. The units are different, so you can't really compare rows, but you should be comparing columns, right? So fixed O&M, this is in terms of dollars per capacity annually, whereas the variable O&M is like cents per amount of energy that you're generating, right? Because this is tied to use, and this is just kind of flat. And so your gas turbines tend to be quite a bit lower than coal, and your coal and oil and steam are usually kind of in the same order of magnitude. Okay, and so there are a whole slew of these different costs that we think about when we're talking about the economics of power plants, right? So the capital cost, the fuel cost, the O&M costs, right? And these are in very different scales, right? Because we could be talking about a 2 gigawatt nuclear plant, and we could be talking about a 50 megawatt solar farm, right? And so these, because you have all these sort of different categories of costs at very different scales, it's often very hard to do comparisons, energy economic comparisons in kind of an apples to apple way. And so one metric that folks in sort of the energy modeling world use is something known as the levelized cost of electricity. And so we take all these costs that I'm just talking about, and we kind of combine them together in a way that does let us do those comparisons, right? And so the average total cost to build and operate a power plant over its entire lifetime, and then you divide it by the amount of energy that it actually produces, that lets you express a standardized like cents per kilowatt hour or dollars per megawatt hour across different plants of very different scales and sizes and fuel types, right? And so this is kind of the general equation for this. I'm not gonna get into all the sort of nitty gritty pieces of this, but essentially you are taking your capital costs and then adding up all over the lifetime of the power plants, all of the other variable costs discounted, and then divided by sort of the energy cost, or sorry, the energy generated in the denominator. And so this is a very useful metric to enable comparisons of technologies that have different lifetimes, different fuel types, that are utilized differently. And it's a useful tool for like developers and policymakers to help identify like cost effectiveness, because I can look at two very different types of technologies and look at how much it would cost for these both to produce electricity for me. Yeah, and so this is very often used in a lot of modeling and policy analysis. But I will say there are some limitations to LCOE to keep in mind. Okay, and so this ignores when the electricity is produced, right? Because we just divide by the total amount of energy. And so electricity has value at certain times compared to others. And so you wouldn't be able to capture that in an LCOE, right? So imagine, let's say that producing power during the day is super, super valuable in some place, right? In which case you might value something like solar producing electricity during the times that you care about more than something that only produces power at like nighttime. It's just a hypothetical example, right? And so LCOE would not be able to capture that in the way that this is formulated. This also excludes system costs, right? And so something like transmission, which could be a big piece of the cost, right? So if I'm comparing two power plants where one power plant can be located right where the demand center is, and you don't need to build out transmission, whereas a different power plant needs to go way out in the wilderness and you have to bring 200 miles of transmission line in order to connect that electricity to the demand source, well, that's not included in your LCOE. Traditionally, there are some versions that do try and include something like that. Yeah, so not a perfect metric, but still something that will allow us to do these sort of rough comparisons, and so typically found to be still pretty useful. So what does that look like in terms of some of the technologies we're talking about? So here's conventional power generation, and so these are all our fossil guys, plus nuclear. And so I was talking about how gas has become economical, and we sort of consider this, right, the sort of gold standard of comparison. And so combined cycle natural gas is right here in a range of like $45 to $74 per megawatt hour. Okay, and we can see how, coal used to be kind of flip-flopped with natural gas, but now has kind of moved up. There are things that are kind of more on this side of, right, so such as gas peakers that provide value that's not necessarily captured in the LCOE that I was talking about, right? So like a peaker plant being able to provide electricity at a critical time, that's why maybe some of these things are still built even though the LCOE is not necessarily pointing to that. And one of the things that you can see, this is definitely a more sort of modern analysis, is that this gold standard that I'm talking about in comparison to like wind and solar, a lot of the renewables are starting to kind of catch up, right? And in this LCOE comparison are starting to even look better than our combined cycle, right? There are limitations to those things, right? Because they can't provide power necessarily at all the times that we want. But from this particular perspective, right, that's one of the reasons why we're seeing the adoption and deployment of those technologies to the extent that we are today.
Is hybrid solar on this trend?
So with hybrid solar, are you talking about like CSP?
No, I mean like solar plus battery.
Solar plus battery? No, I don't think they have that on here. Yeah. That would just be like one of these guys and then toss in the extra cost of the battery. Because the battery is not really going to change the economics from an LCOE perspective, besides adding cost, unless your system is getting curtailed a lot, which means that, yeah, exactly. In which case the E in the denominator would go up. But usually that's not necessarily the case. So, yeah, and that's where we're kind of pointing to some of the shortcomings of the LCOE a little bit. Yeah, and like the rooftop, right, looks really expensive, but with a rooftop, I don't need any of the like transmission system to be built, right? And that's usually not included in the LCOE. So there are like some of these nuances and benefits that aren't gonna come out in this metric. So it's not a perfect metric, but still it's one that's pretty good at what it does, and is pretty commonly used in in the field. Questions? Okay, so we are going to close out today. Lastly, thinking about impacts of fossil plants and mainly focusing on sort of the emissions. So I've talked a little bit touching on sort of the localized impacts, and those are important and shouldn't be sort of dismissed, but oftentimes when we think about sort of the broader social impacts of these fossil plants, emissions, emission byproducts are usually going to dominate in terms of the like harms to society. So power plants, they're the largest stationary source of air pollutants globally. We're going to think about pollution in two categories, okay? So you've got pollution that affects the climate, right? And so these are your greenhouse gases. And then you have pollution that affects local air quality and thereby like local human health. So these are going to affect human health outcomes. And so examples of climate forcers are going to be carbon dioxide, methane, N2O, and then examples of local air pollutants are going to be NOx, SOx, and particulate matter. So NOx refers to nitrogen oxides. It could be NO3 is the most common, I think, and then NO4, and then SOx is sulfur oxides, SO2, SO3, and then we'll talk in more detail about particulate matter in a second. So the pollution comes from the direct combustion process, and so those are things that I was talking about primarily, right? With hydrocarbons, you're talking about carbon dioxide, but then you also have combustion byproducts, right? So these are things that are a result of the impurities in your fuel or in your air, or resulting from incomplete combustion. And so all of these are going to lead to outcomes that we care about. So what are the main pollutants from fossil plants? So CO2, that's the main one, right? That's the primary byproduct. You're unavoidable through any combustion process, right? Because you are essentially combining your hydrocarbons with oxygen, and that's your kind of main outcome. And this is a known climate forcer, right? So greenhouse gas, which will lead to global warming, and other sort of climate impacts. You have NOx, which results, as I was mentioning, right? You have nitrogen in the air, and in the presence of oxygen and high temperatures, you can get chemical reactions to form nitrous oxides. This is ozone, smog, acid rain, all these things that you guys have probably heard of that can lead to poor health outcomes. SOx, so sulfur. So the primary place this comes from is coal. Okay, you're not really going to see SOx coming out of combustion from natural gas. And that sulfur, if you guys remember all the way to the beginning of lecture, we had that molecule of carbon, right? You've got sulfur is a very common atom in those molecular structures, and so you tend to see this happening with coal combustion. Particulate matter, this is usually incomplete combustion and from impure products in your fuel-air mixture. And then other like heavy metals, mercury, that sort of thing, that's usually all the impurities that are associated with coal as well. These types of things you're not really gonna see with natural gas. Okay, so I've been mentioning particulate matter a couple times. So what is particulate matter? So this is a mixture of solid particles and liquid droplets in the air, and we describe particulate matter based on categories of size, okay? And so you guys may have heard of something like PM10. So this is more coarse particulate matter, and that refers to things that are 10 micrometers or smaller. PM2.5 is what's known as fine particulate matter, and these are particles of 2.5 micrometers or less. So this is a nice little diagram that shows kind of relative scale. So the blue is PM90, and that is the size of a grain of sand. Okay, the green circle there, that's PM50, and that is the relative size of human hair. The yellow circles, those are PM10, and that is the size of like dust, pollen, mold, so common things that you might run into. And then these little white dots here, that's PM2.5, and that is in reference to like soot and some of the other combustion byproducts. So PM10, dust, pollen, mold, your body actually does a fairly good job of filtering that stuff. That when you breathe and you breathe in PM10, a lot of that is going to get captured in your like snot and saliva and respiratory, or before it hits your respiratory system. PM2.5 is going to go straight through all of that. So that's going to get deposited into your lungs pretty easily. Our body does not do as good of a job of filtering 2.5, and so that can lead to lots of bad outcomes, respiratory outcomes. It is often considered carcinogenic, and PM2.5 is known to account for millions of excess deaths worldwide. Okay, it's the 5th leading risk factor for dying on average across the world. Typically speaking, the dirtier your combustion is, the worse the PM outcomes are in terms of how much get emitted. In the US, this is kind of daily average PM concentration. So this was a decade ago. Things I would say have not changed too much. There was kind of a big dramatic drop in these concentrations back in the like 70s, 80s, maybe even early 90s as pollution controls were starting to get enforced from the EPA. But this is kind of what it looks like today. A lot of this stuff here is coal plants. And then in California, a lot of this is derived from combustion in like the LA area, both power generation, but also transportation. And because of the geography of California, a lot of that local air pollution will flow down into the Central Valley and kind of spread out throughout Central California. Yeah, and so this is what PM 2.5 concentrations look like, relatively speaking, in the US. And you guys can go and look at maps of the rest of the world if you're interested in kind of looking at distribution of this stuff. Yeah, it's bad in a lot of countries that basically take advantage of fossil fuel combustion, and so there's a lot of places that have like very perpetually bad PM 2.5 concentrations in like big cities in China, big cities in India, and that is the cause of a lot of those excess mortalities that I was just mentioning. Yeah, so in terms of SOx, NOx, and particulate matter, what do those look like coming from different fuel technologies? Coal tends to be pretty bad, right? CO2, SO2, NOx, and particulates, although with some of the more advanced controls, you can see those numbers get dropped down very significantly, right? So by an order of magnitude. But at the end of the day, natural gas tends to be much cleaner, right? So you don't get very much particulate matter, you get very little, or basically no SOx, as I was mentioning. There's a question?
Yeah, is carbon capture what you mean by control?
No, these, this is, what does SCR stand for? These are like certain types of scrubbers.
Selective catalytic reduction.
Yes.
Selective catalytic reduction.
Yeah, thank you. So these are, like, think of your muffler in your car. It's operating in a similar type of way that is able to, it's able to use these catalysts to essentially undergo certain chemical reactions that lowers the activation energy to reduce the concentration of these guys. And so, yeah, with some of these pollution controls, not CCS, which is mainly for CO2, you are able to reduce this stuff. And CCS, I should say, yeah, it's not something that is necessarily addressing these other byproducts of combustion, but by virtue of those facilities kind of being newish and state-of-the-art and that sort of thing, they will often be coupled with more advanced pollution control systems. So this right here, 1 kilogram per kilowatt hour of CO2 compared to natural gas, like 0.4 to 0.5 kilograms per kilowatt hour. That's a big difference, right? You're talking about half the CO2 emissions in comparison to coal. And so whether or not you like natural gas, right, as you know, we're in a energy graduate group where we tend to like clean technologies, very pro greening of our electricity system, and so like the fact that natural gas is a fossil fuel, maybe some people think that automatically makes it bad, but kind of whatever you think about natural gas, this fracking phenomenon that has led to a transition from coal to natural gas has by far led to a larger emissions reduction across the sort of US economy than any other thing that we've done, right? It's not renewables, it's not like electric cars, like coal to natural gas, that halving of emissions is the thing that has made the largest impact in the last 2 decades from a carbon reduction standpoint. Okay. Yeah, and so a lot of the technologies that are associated with pollution controls are a sort of direct result of Clean Air Act and regulations that kind of spun out of the Clean Air Act, right? So power producing companies, all of the pollution, that's externalities. It's not necessarily something that they are tied to or required to deal with before the regulations came along, right? That's just extra cost to have these pollution controls and implement these technologies. But sort of as a result of a number of very pretty substantively important programs, we've reduced local air pollution quite a lot. And so you can see there are these animations of these pollution concentrations that you can see over the years. And these programs played a very substantial role in helping alleviate those local air pollutant emissions. Yeah, and so that progress, the progress that I was talking about with natural gas, you can see kind of most directly here. And this will correlate to other sort of air pollutants too, because of how relatively dirty coal is compared to natural gas. And so you can see as electricity demand and corresponding generation increase, that's kind of lockstep with an increase in CO2 emissions, right up until this period in which we started transitioning to natural gas. And so electricity generation looks like that, but CO2 is kind of dropping down. Okay, any questions about any of that? Okay, so key takeaways for today, right? So all fossil plants rely on translation of heat in order to spin a turbine and generator to produce electricity. And so the kind of categories of things to think about are the differences in operations between the different fuel types, right? Coal and oil being sort of slower and for steadier output. Gas is fast and more responsive, and then combined cycle is now a more sort of dominant technology in terms of kind of baseload generation. The economics are what drive that a lot, right? Capital intensity of coal is much greater than natural gas. And then at the point at which gas started to dominate in terms of fuel costs, that's when we started to see this big transition away from coal. And then emissions, with anything where you're doing combustion, really you can't get around this. So CO2 is inevitable, and that's why, as climate change becomes more of an important issue, we're starting to transition away from this broad set of fossil plants. But, right, as I was mentioning, natural gas is still very compelling in comparison to our sort of old way of doing things with coal. And then pollutants have been not eliminated, but dealt with pretty well with a lot of the controls that exist now. But those do add costs to these plants. Yeah, and that's it for today. And so I will see you guys not next week, but in 2 weeks, right? Because I'm going to be out of town, but the lectures are going to be recorded and posted online. So make sure to watch those before we come back. And then today, we're Tuesday, Thursday. Okay, yeah, so then we don't have to worry about that. Okay, cool. Thanks, everyone. See you guys in 2 weeks.